Hi, I'm Jim Burnham, and welcome to Naming Chemical Compounds. My name is not Inigo Montoya, but we are going to talk about how to name chemical compounds. Except for the noble gases, most elements in nature are found in combinations or in compounds. And those compounds come in two basic varieties. Molecular compounds, like water, which is two hydrogens bound to one oxygen, or ionic compounds, which are large crystalline arrays, salts, and they're formed by positive and negatively charged particles coming together. Now, most atoms exist in the form of molecules, which is the smallest electrically neutral unit of a substance that still has all the properties of a substance. So, for example, every molecule of water still has all the properties of water. So a molecule is two or more atoms acting together as a unit. Here is a molecule of oxygen, here's a molecule of ozone, and of course they don't all have to be the same, we can mix and match them. Most molecules are composed of two or more non-metals. This is important because we're going to also talk about compounds that are built out of metals, and those typically are ionic compounds. The non-metals are these guys right here, to the right and top of the periodic table along with hydrogen. But not all compounds are molecular, built out of these non-metals. Many compounds are composed of particles called ions, and their compounds are called, unsurprisingly, ionic compounds. Now, an ion they're atoms or they're a group of atoms that have a positive or a negative charge. How do ions form? Well, by gaining or losing electrons. So every atom starts out as a neutral atom, and if it loses an electron, then it has a net positive charge because it lost that negative charge of the electron. Or if it gains an electron, it gains a negative charge. And a positively charged ion is called a cation, and a negatively charged ion is called an anion. Metallic elements like sodium tend to lose electrons. And so, for example, here's sodium. It has one electron in its outer shell. It's known as its valence shell. And that electron is easily pulled off and becomes a positively charged sodium ion. That forms a cation, positive charged ion. So you lose an electron, you form a cation. You gain an electron, you become an anion. Cation then is an atom or a group of atoms that has a positive charge. And we can remember that by writing the T of cation with a plus sign. So cation, positive charge. And we can remember anion is a negative charge if we just remember this N in the middle here is an N for negative. So how do we name cations with a positive charge? Well, that's pretty simple. The metal ions are the name as the element name. So here's sodium metal. When it loses an electron, becomes an ion. We call it the sodium ion. So that's fairly simple. It's not quite as simple as the nonmetals, but for the metals, the ion name is the same as the element name. Now, non-metallic elements, these are the ones over here on the right and top of the periodic table. These tend to gain electrons, unlike all of these metals. Metals tend to lose electrons, non-metals tend to gain those electrons and form negatively charged anions. So an anion is simply an atom or a group of atoms with a negative charge. And we try to remember that with the N here, the plus here, the N there. How do we name anions? So I'm going to put a negative charge here by my N for negative anions. We take the name of the atom and we change the ending or the suffix to "ide." So here, for example, is nitrogen. Well, when it becomes its ion, we call it nitride. Oxygen, oxide. Fluorine, fluoride, and so on. So we're going to take the name of the atom and change the ending to "ide. And then we usually follow up by saying ion or anion. So what do we do with positively charged cations and negatively charged anions? Well, we build ionic compounds, which are electrostatically attracted complexes. The positive charge and the negative charge attract each other like poles of a magnet, and it holds these compounds together very, very strongly. So those are ionic compounds. For example, here's salt, table salt. It is made up of the positive charged sodium ion, and the chloride negative ion, and these are held, they form a 1-to-1 ratio in this giant crystalline network. And so we call it NaCl. This actually, as we see later, is a formula unit. It's a way of describing the ratio of this ionic compound. So ionic compounds are built out of cations and anions, positive and negative charges. Usually a metal cation and a non-metal anion. So since we have two different kinds of compounds, molecular compounds and ionic compounds, we should expect to have two different kinds of formulas and also two different ways of naming those formulas. So molecular formulas are going to correspond to molecular compounds, and ionic formulas are going to correspond to ionic compounds. And these ionic formulas are usually called formula units. So molecular formulas give us the chemical formula of a separate molecule, like water. It shows us the kinds and the numbers of the atoms present in the molecule of the compound. So here we have, with the subscript here, it tells us we have 2 hydrogens bonded together with 1 oxygen atom. And this together is a molecular unit, a molecule. Here's another molecule. This tells us this is 2 carbons bonded together with 6 hydrogens, called ethane. For ionic formulas, we use something called formula units. Now they're going to look very similar to molecular formula, but it doesn't represent a molecule, because ionic compounds don't make separate molecules, but a continuous array of ions, a giant network lattice of ions, like this. So you don't see little discrete separate molecules. What you see is a giant lattice work. And so the easiest way to describe this is to describe the ratio of one of these, say, red balls to one of these, or one or more of these green balls. So we call that a formula unit, which is the lowest whole number ratio of ions in the compound. So in this case, salt, it's a 1-to-1 ratio. For every sodium, there's a chlorine. And so the lowest whole number ratio is 1-to-1 NaCl. That's our formula unit for this ionic compound. Well, how do we know an element's ionic charge then, especially for building ionic compounds out of ions? Well, for monoatomic, that's single atoms, we consult the periodic table. The periodic table in its groups tells us the usual ionic form of the various elements. So everything here in group 1 is generally going to form a +1 ion. Group 2, a +2 ion. We'll skip these transition elements. Group 3, a +3. Group 4, either a plus or -4. Group 5, now these are going to be trying to become like noble gases, so they're going to gain electrons. So up to this point, they've been giving away electrons, but here they're going to start gaining electrons. So this is going to gain 3 to become like neon. This is going to gain 2, gain 1. And so these are typically going to have a -3 ion, -2 ion, -1 ion, no ion here. The noble gases tend not to form ions. They have a complete octet in their outermost shell of electrons, called the valence shell, and they don't want to gain or lose electrons. So as you can see, if we represent the outer shells, the valence electrons, you can see what's going on here. These are trying to get rid of 1 or 2, or in this case 3 electrons, so they can become more like helium, more like a noble gas. These want to gain 3, then 2, then 1 electron to become like neon, the closest noble gas. Notice that the majority of the elements in the 2 representative groups 4a and 0, or the noble gases, tend not to form ions. So that's this group here and this group here. Group A elements, group 8A, that's the noble gases, rarely form compounds. And carbon and silicon are usually found in molecular compounds. Now, unlike groups 1A, 2A, and 3A, many transition metals have more than one common ionic charge. Remember, the transition metals are these metals in the middle. So this is 1A, 2A, 3A. So these are the A's, skipping over this group here, and these are the B's. And these transition metals, they form positively charged cations, as you expect, but many of them form more than one form, and so we have to keep track of that. Copper, for example, forms copper 1 and copper 2. Iron forms copper 3 and copper 2 and copper 3. So, yes, iron, for example, it forms two common cations, a +2 and a +3. How are we going to distinguish those? Well, we have a method called the stock system, and this is a newer and more elegant system than the older system, which we won't talk about today. But this one uses Roman numerals to distinguish the various kinds of ions. So if this is the +2 ion of iron, we're going to designate that with a Roman numeral 2. And the 2 corresponds to the +2 charge. The 3 here corresponds to the +3 charge on this ion. And unlike this space here, when you write these, you don't want any space between them, between the element's name and the parentheses. There's no space. Remember, we only use this for metals that form more than one ion. If it only forms one, you don't use the Roman numeral. Remember, the Roman numeral tells you the value of the charge. Okay, so you see that Roman numeral. You don't have to. If it's a 2, it means it's a +2 charge. If it's a 4, it's a +4 charge. It tells you the charge of the cation. So iron +2 is iron 2. Notice no space, ion. Iron 3, ion. Here are some metals that form more than one monoatomic ion. Chromium forms a +2 and a +3. We designate that with a 2 and a 3 in the Roman numerals. Cobalt forms a +2 and +3, same thing. Copper forms a +1 and a +2, so we designate it that way. Iron, as we saw, a 2 and a 3. Lead, a +2 and a +4, and so on. There are a few transition metals that only have one ionic charge. That's great. So would we still use a Roman numeral for them? No, of course not. It's unnecessary. These exceptions include silver, which tends to be a +1, cadmium, which is a +2, and zinc, which is another +2. Okay, so remember, we use Roman numerals only for ions, not molecules, and only for ions with multiple charges. So if it's an ion with a single charge, like silver, we don't use a Roman numeral. Okay, that takes care of monoatomic ions, but what about polyatomic ions? Remember, mono means one atom, but poly means many. So we're talking about ions built out of multiple atoms. The definition of a polyatomic ion is a tightly bound group of atoms that behave as a unit, and as a unit, they carry a positive or negative charge. So here are some common examples of polyatomic ions. Here's ammonium, NH4 with a positive charge. Here's nitrate, NO3 with a single negative charge. Here's phosphate with a triple negative charge, PO4, 3 negative. Sulfate with a 2 negative charge, SO4. And remember, that -2 is part of this whole unit. It's not like it just belongs to the oxygen. It belongs to the whole poly. So the positive or negative charges belong to the group as a whole. These are some of the polys that you should memorize, and we've talked about memorizing them. You can do it. In fact, you must do it. We'll see why a little bit later. Gotta memorize the polys. Dude, you can do it. How do we write formulas for binary ionic compounds from their names? Starting with a name, how do we write a formula? So for example, how do we write a formula, a chemical formula for potassium chloride, which is an ionic compound, and it's composed of potassium ions, cations, and chloride, negative charge, anions? Well, we always write the cation first. Remember that. Cation first. So we're going to put the cation down with its charge, and then we're going to put the anion down with its charge, and then we're going to make sure that the net ionic charges come to 0, that they balance each other out. When I add them together, they equal 0. So this positive charge is balanced by this negative charge. In this case, it's just a 1-to-1. I need one chloride to balance out one potassium. And so I get potassium chloride written as a formula unit right here. So here's a way you can think about it. Think cab. Cation, anion, balance the charges. Cation, anion, balance the charges. Say it with me. Cation, anion, balance the charges. Okay, let's try calcium bromide. Calcium is a +2. We can see that from its position. It is a group 2 metal. And bromide is a -1. We can see that from its position as one of the halogens in the group 7. So now we're going to list them. So we've got cation, anion, balance the charges. How many bromides are we going to need? Oh, so cation first, right? How many bromides are we going to need to balance out the magnesium? I guess here calcium. I guess we were doing calcium for a second. Well, it doesn't really matter. So going back, we need 2. This is a +2 charge, so we need two negative ones to balance this out. So cation, anion, balanced charges. Calcium bromide. How about rust? Well, rust is iron 3 oxide. And what does that 3 tell us? That it forms a +3 cation. So we put the +3 iron here on one side. That's the cation. Here we know that oxygen forms a -2 because it's positioned in the periodic table. And now we're going to use what's called the crisscross method to balance the charges. I'm going to take the cation superscript here and bring it down here as a subscript for oxygen. And I'm going to use the oxygen -2 charge and bring that as a subscript over here for the iron. And I'm going to end up with Fe subscript 2 and O subscript 3. It looks like this. And that tells me that I've got 3 -2 charges for a total of -6, balancing out 2 +3s for a +6. So my overall charges balance 2 +3s and 3 -2s. So that's how we go from names to formulas. How about the reverse? How do we go from formulas back to names? So let's try copper oxide. So this is copper, and it's an oxide because it's combined with oxygen. How do we name this? How do we give a written name from this chemical formula, this formula unit? Well, we know that the oxide ion always has a -2 charge because of its position in the periodic table. That means the copper cation must have a +2 charge in order to balance oxygen's -2. And since copper is a transition metal with more than one ion, we have to use a Roman numeral to designate which form. So it's going to be, in this case, copper 2, because it has to have the +2 to balance out the -2 of the oxygen. And so our written name would be copper 2 oxide from this formula. Does that make sense? Let's try another one. How about this? This is Sn is tin, and this is an oxide because it's formed with oxygen. So what is this? Well, let's work backwards. Work from the anion backwards. We know that oxygen forms a -2 charge. 2 -2s is a -4. So this whole thing has a -4, and it's counterbalanced by 1 tin atom. So that tin atom must have a +4. Therefore, this must be, and tin forms more than one transition, for more than one kind of ion, so we're going to need to use Roman numerals, the stock system, to designate which form of tin we have. So we know it has to be tin with a +4 charge, therefore we're going to designate it as tin, no space, 4, oxide. Notice we don't have to designate that there's 2 oxygens, because when we build this back up, we know that there's going to have to be 2 oxygens to counterbalance this +4 charge. So this is just tin 4 oxide. Okay, we've looked at monoatomic ions and binary ionic compounds. So right here, this is a binary, right? It's built out of 2 different kinds of atoms. What about ternary ionic compounds? So mono means 1 atom, binary means a compound built out of 2 atoms. As you might expect, the word ter means 3. So here's some examples. Calcium, for example, is a monoatomic ion with a +2 charge. When it combines with chloride, it forms a binary compound. And here is calcium forming a bond with two other atoms, so that we have three different types of atoms. This is a ternary compound. A ternary compound. Well, that means three different elements. And here's the giveaway. Usually a ternary ionic compound contains a polyatomic ion. In this case, it's our carbonate. You should remember that if you get rid of this cation here, what you have left here is a carbonate, a polyatomic ion with a -2 charge. And that's why we have one polyatomic combined with its -2 charge, combined with this single calcium with its +2 charge, making calcium carbonate. But if you didn't recognize that this was a polyatomic, you might try to name this something like calcium carbon oxide or something like that, which is wrong, because this functions as a group, has a charge as a group, has a separate name. And that's why we have to memorize the polyatomics. So, yeah, we memorize them so we can recognize them, so we're not fooled when it comes to naming them. We name polyatomic ions, the same way as binary ionic compounds, right? So we keep track of the formula and the charge of each ion. Then cation first, anion second, balance the charges, Ca, right? Cation, anion, balance the charges. In this case, we just have a polyatomic anion, but it's the same thing. Cation, anion, balance the charges. Here is something to remember about polys. Many of them end in ate or ite. And that indicates a poly with oxygen. So if you see ate or ite, so here's carbonate, right? Carbonate means that it's carbon with an oxygen. So that is important to recognize. If it's an ate or an ite, it's going to be a poly with oxygen. Okay, what would be the formula for lithium carbonate? Well, what's the charge? Lithium's a group 1, so it's going to be Li+1. Carbonate, as we saw, is a poly. It's going to be CO3 -2. So how many lithiums are we going to need to balance out the -2 charge of the carbonate? Well, obviously we need two. Two plus ones equal a -2. And so when we write this, we're going to have a subscript here. We're going to write lithium. I need two of those guys to balance out my whole polyatomic. Remember, this polyatomic we keep as a group. We don't. If we change something on it, we change everything, or we change it as a unit. We'll see how in the next compound. For example, calcium nitrate. Okay, cation +2. The whole poly is the anion. This is nitrate. Notice we have a +2 charge. How many nitrate units are we going to need to balance that out? Well, each unit is a -1, so we need 2 whole units to counterbalance the +2. We need 2 whole nitrates to balance out calcium. And so we write that this way, calcium, and then we use parentheses. We put the nitrate inside to protect it, because it functions as a unit. And then outside the parentheses with another subscript, we designate this is how many polys we have. We have 2 nitrates combining with each calcium, because I need 2 polys to counterbalance this +2 charge. Just one won't do it, so I need 2. Okay. When naming ternary ionic compounds from the formula, you must recognize the polyatomic ions, or you will have chaos. So look at this one here. What you should, when you look at this, instead of being, first you should say, well, this has got how many different kinds of atoms? 1, 2, 3. So this is a ternary compound. And remember, ternary compounds usually have a polyatomic attached. So this is our metal, which was what we'd expect with any kind of ionic compound, a metal plus something else. So we should recognize this as 2 potassium ions combined with 1 polyatomic anion called dichromate. So don't break this down into something else. This is a freestanding separate unit called dichromate. So what would this be called? Potassium dichromate. How do we name binary molecular compounds? We haven't talked about molecular compounds. We've been focusing on ionic so far. Well, unlike ionic compounds, binary molecular compounds are composed of two nonmetals. Remember, ions have a metal and a nonmetal, but molecular compounds have two nonmetals, a nonmetal and a nonmetal. So we're not going to use ionic charges to assign molecular formulas or names. Remember, ionic charges only apply to things with charge, like ions. Remember, molecules are electrically neutral, so we're not going to use ionic charges when it comes to dealing with molecular formulas. We don't do that here. Also, when two nonmetals combine, they often do so in multiple ways. For example, when carbon combines with oxygen, it can form two different kinds of gases. The poisonous, odorless gas, carbon monoxide, and the completely non-poisonous, somewhat helpful gas, carbon dioxide. How do we tell them apart? Well, we can't just call them both carbon oxides, which they are, but that doesn't tell me which one is dangerous and which one is not. So we have to have some other way to name them to tell them apart. And that one-word way is called prefixes. We're going to use prefixes to tell us the number of molecules that we're dealing with. Mono is going to be 1, di is 2, tri, tetra, penta, hexa, hepta, octa, nona, deca. We only use prefixes for molecular compounds. It's super important to remember that. Okay, we use prefixes for molecular compounds, we use formula units and charge balances for ionic compounds. Don't try to confuse those two methods. Charges for ionic compounds, prefixes for molecular. So, this we call carbon monoxide because we have one oxygen. This we call carbon dioxide, that should be a subscript. Carbon dioxide, where we have two oxygens. Now you might say to yourself, well, wait, why didn't we designate the number of carbons? Well, if it's just a single atom in the first element, we usually omit the prefix mono. So we call this carbon monoxide, we don't call it monocarbon monoxide. We leave out the mono because if the first one is singular, then we leave out the mono because it's understood to be single. Now, if it's two or more, then we bring in the prefixes. So here, for example, nitrogen monoxide, not mono-nitrogen monoxide, nitrogen dioxide. But now, if we go to 2 in the first one, dinitrogen trioxide, dinitrogen tetroxide, and so on. So remember, binary means it contains two elements. Ternary means 3. Remember this, all binary molecular compounds end in "ide," which is the same rule we found for the binary ionic compounds. So here's the general rule, all binary compounds, whether they're ionic or molecular, end in "ide." If you see "ide," think binary compound. Could be ionic, could be molecular, but it's binary. Okay, how would we write the formula for carbon tetrachloride? Well, that's 1 carbon and tetra, 4 chlorides. So we write carbon and 4 subscript chlorides. How about tetra, 4 iodine, and non, that means 9, oxygen? Well, I4, O9. So you can see that the subscripts here correspond to the prefixes. The prefixes give us the subscripts. And if we're going backwards, then the subscripts give us the prefixes. This would be tetra, iodine, non-oxide. So we can practice some of these. We've already seen this. So this would be sulfur dioxide, sulfur trioxide, dinitrogen tetroxide, and so on. Okay, so when writing a chemical formula from a chemical name, follow these rules. For ionic compounds, we have to balance the charges to 0. So the charge on the cations has to equal the charge on the anions. Remember that an "ide" ending generally indicates a binary compound. It could be binary ionic, it could be binary molecular. An "ite" or "ate" usually means a polyatomic ion with oxygen. And prefixes generally indicate molecular compounds. And the prefix gives you the number of each kind of atom in that molecular compound. And the Roman numeral after the cation shows the ionic charge. Again, we're only going to use Roman numerals when it comes to ionic compounds. So let's try some combinations here. So what is this? Well, this is, you should recognize this as a polyatomic ion named cyanide. This is a polyatomic ion named phosphate. This is tin plus 4, so that's going to be a tin 4, because we know that tin has more than one ionic form. And this is magnesium. We don't use a Roman numeral because magnesium only comes one way, plus 2. So when we combine these, which one's going to go first? Well, cation's always first. Cation, anion, balance the charges. Cat, right? Cation. So we're going to put this. We're going to put the tin here. It's a plus 4, which means we need 4 cyanide. So this is going to be Sn, and then with parentheses Cn minus, and then a subscript 4 here to indicate we need 4 of those polys to balance out the charges of the tin. And we would name this, when we wrote it out, as the name tin, parentheses 4, cyanide. So here's how they'll look. Okay, tin 4 cyanide. Here, how about we combine tin plus 4 with phosphate negative 4? We're going to use the crisscross method. The 3 is going to come down here as a subscript here. The 4 is going to come down as a subscript here. And, the 4 is going to come down as a subscript here. And we're going to get tin 4 phosphate. Here's magnesium. We need 2 cyanides to balance, so we're going to have cyanide 2 balancing out magnesium cyanide. Again, crisscross, we're going to put the magnesium 3 and the 2 over here, and this is magnesium phosphate. Easy peasy. Okay, quick summary. Ionic compounds. Cation, anion, Roman numeral. If it's one with multiple charges, balance the charges. So cation, anion, Roman numeral if necessary, balance the charges. Molecular compounds, no mono if the first atom is single, and then go crazy with prefixes after that. Thank you for your attention.